Hello, we're Group 4. My name is David Hilton. This is Carolynn Rendon and Alfredo Mere, and our robot design project is Robots in Space.
So robots in space. Mainly, robots are being used in space nowadays to perform actions that humans can not perform or not perform as efficiently. For example, like position instruments and to take measurements, collect samples for examination, to assemble structures, or to move around astronauts with their equipment. Advantages of using robots in space is that since they don't need food or water, they can work around the clock and they can operate in very inhospitable conditions that humans would be limited to be exposed to. Some of the challenges that we face when putting robots in space is that due to the ultra-high vacuum felt in space, the use of lubricants is very limited between joints and machinery. So that has to be taken in consideration. Also, due to cold temperatures, you might have some cold welding between metal parts. And since the temperatures can swing widely depending on whether the robot is in the sunlight or the shade, one can also be exposed to very high temperatures. Since having no gravity, one can have concepts that would not be possible on Earth, like picking up extremely larger pieces for a smaller robot. And in space, since they weigh less, that could be possible that the small robot could perform such tasks. And they can also, in space, withstand a higher fault tolerance due to the gravity not being affected. Like for example, if one of the joints is about to fall off, it will not be as detrimental as here, but you can also go over the board with that.
Okay, some applications of some robots in space. We can do stuff like driving and flying. A lot of driving is used in space. We're landing on the moon and landing on Mars. The Mars Rover mission, the robot's got to be able to drive, fly, land. A lot of small body orbiting. Our robots are orbiting around the Earth constantly. Subsurface access. We have onboard science, user interfaces, some simulations, construction, sampling, and instrument placements. The Canadarm robot. This is a robot that has flown on every single space mission for the last 20 years. It has a 2-degree freedom shoulder, a 1-degree freedom elbow, and a 3-degree freedom wrist. It's routinely used as a mobile work platform for the astronauts. It does stuff like tossing satellites into space and retrieving the faulty ones. It gets the satellites back into orbit if they get out of orbit and whatnot. Some non-routine uses that this robot has done in space is done stuff like knocking a block of ice from a clogged water waste vent. It's also pushed a faulty antenna back into place and activated a satellite that failed to go into proper orbit. Okay, we also have a Lunar Robot here. As you see in the picture, we have 2 robots. On space, what they can do is they can grab the container in the middle, pick it up, and move it over. Robots in space, like these robots, are very large, and they can pick up a lot of weight. They they do it very slowly. It takes a lot of precision to be able to pick it up and move it, so it takes some time to be able to do this.
Okay, another aspect of robots in space is exploration to planets that humans cannot yet travel to. One of these planets, which has a lot of people interested in, is Mars. You can see some of the pictures here of robots being designed for Mars. Now, robots are the ideal explorers for humans in this case because Mars is so far away that we don't have the logistics to really get there. We have to transport someone there. We have to have air for them, food, water, and then we have to have a way to get them back. Robots, we can send them on a one-way trip, and they don't complain. Okay, this is a new project, the Mars Exploration Project. It was launched on November 26th of this year, so it's very recent. It was about 5 days ago as of this recording. The laboratory rover, its job to go to Mars is to collect samples, gather telemetry about the planet, learn as much as they can about the atmosphere and what elements are available there, and basically determine long-term habitability of Mars. Basically, NASA wants to see if they can colonize the planet.
slides up.
Okay. This is a picture of the Mars Curiosity robot. You can see it's a very large robot by its size, and it also has a manipulator arm on the front end. This manipulator arm is what gave us our idea for our project. Okay, here's a conceptual picture of this robot when it would be on Mars. Okay, for our conceptual design, we looked at two different designs. We looked at the 3R robot, and we also looked at an RPR robot. That's rotational prismatic, then rotational robot. We decided to do the 3R robot because of its flexibility. It works much like an elephant truck, where it can grab down and fold up over the robot itself. It can fold onto itself for storage with the joints overlapping each other, but on the sides. And one of the reasons we did not choose the RPR robot is because it would have interference when loading rock samples into the bin, which you'll see on the conceptual design of the robot. This is just a picture of the alternative design, the RPR robot. You'll notice it has a rotational joint at each end, one at the body of the robot, and then one at the manipulator claw. And then it has a prismatic joint in the center, which would allow it to extend or contract to reach samples farther away from the robot. And this is a design, our proposed design. You'll notice that the bin is located on top of our rover, our theoretical rover, and it has 3 joints with 3 rotational links there, there, and there, which allow the robot to have maximum flexibility for whatever mission we need it for.
Okay, so we chose the 3 degree freedom 3R robot. With the calculations with this, what we decided to do is go ahead and choose the path that we wanted the end effector to do. So we wanted it to pick something off the ground, and like an elephant truck, like David said, is bring it up and over and then drop it into the back of the trunk. What we did is once we picked the path that we wanted to, the end effector to go through, we did inverse position to find the joint displacements of each point along the path of the movement. Some of the graphs we have are theta versus our point. So each point on our graph, on the last slide, this corresponds to the angle of each of the joint displacements. This is the side view. Like he said, the arm comes over, it comes up, over, and drops. You can just drop it in the bucket. The top view. This is one of our first animations. This is the one that we went with. Picks up the rock, brings it over, all the way back, and then it just, right there, can drop it.
This is just the forward movement of it. Let's say in the other one we had noticed how you can drop it. Now in this one you can gently place it into the bucket, meaning if you have like a fragile sample or something like that, so you have options. So the main uses of our design robot is basically to collect samples, may them be rock samples or whatever it may find. And also, it can also be used alternatively to set up equipment, similar like to the claw on the space shuttle, even removing ice, or just can help push rovers around, or just place things where they should be. So, as a conclusion, we can say that since robots can be used to do things that humans are not capable of doing, or do it more efficiently throughout the clock or more hostile conditions, robots in space are being used and more, so engineers are coming up with better technologies and better ways to provide better robots to work out in space.
Thank you.
Thank you so much.